Okay, so I'm back. I did the magnetic field due to a long straight wire, and I did it two ways. I did it with the normal traditional way where you break it into pieces, let the piece size go to 0, add them up as an integral, and so I did it that way. And then I did the approximation to that solution as the magnetic field location is close to the wire, and then I did it numerically. I did it numerically in Python, but actually breaking it into 100 pieces and finding the magnetic field due to each piece. So this is where we're going to do the same thing for a loop of wire now. So still we have this. This is the law of Biot and Savart. This says the magnetic field due to moving charge Q with the velocity v. You can find it with this, where that's the cross product between QV and R hat. R hat is the unit vector from. So here's let me switch over here to this version too. This is the tiny piece of current version. So if I have a piece of a wire, dl, and that's a vector, it has to be in a direction, and I have a current I, then I dl cross r hat would give me the magnetic field at this location. So that's the r hat is the unit vector from the piece to the observation location. And so that's the cross product. And then I divide by the magnitude of that squared, and then I have this mu naught over 4 pi, which is the magnetic constant, where mu naught over 4 pi is 10 to the negative 7th exactly. So what I'm going to do in this case is I have a loop of wire that has a current going around in it. I want to find the magnetic field along the axis of the loop, which I'm calling the z direction. It's a loop of radius r, and this is the result, which I have little dots there because I didn't take a picture correctly. So the magnetic field of the loop along the axis in the z direction, because that's just that's the scalar value, is mu naught over 4 pi, which is that constant, 2 pi r squared I divided by z squared plus r squared to the 3/2. So let's switch over to the paper and let's do this. Let's see if we can get that same answer. And then I'll take a loop in Python and break it into 100 pieces or so, or however many we want, and see if we can get the same thing. And I'll show you why that's a little bit more powerful in this case. Okay, switching over to paper. Paper time. Okay. So let's just start with our loop. Let me just, for simplicity, draw the loop like this. Okay, so that's the z direction. I got a little wire right there. That's the z direction, and this is my loop of current. So in this case, let's say it's coming out. It's coming out of the paper right here and going in. So I've cut away the loop. It's really a circular loop like that, right? But it's going in and out that way. But I just cut it that way so we could see it a little bit better and work on it. So here's my observation location. So this is the distance z. And I want to find the magnetic field due to just a piece of the wire, this little piece up here. So I want this is my vector r. Okay, so no, I'm sorry. That's r. I was skipping ahead. Okay, so that's my piece r. Let's go ahead and say what direction. I want to find out the magnetic field due to just this piece right here. I'm going to call that dB. So dB vector is going to be mu naught over 4 pi times I dl, which dl is the little piece of the wire right there, cross. In this case, I'm just going to put, I feel like putting just r. Let's just put r. And that's divided by the magnitude of r cubed, right? Because r hat is the vector r divided by the magnitude of r. So if I replace r hat with r over the magnitude of r, then I get r cubed on the bottom, and it all works out in the end. So in order to do this, I'm going to need to get a vector expression for dl and a vector expression for r. Okay, so let's start with dl. dl, since this is coming out, this is the z direction. So let's see if I call this the y direction and this the x direction. No, let's call this the x direction and this the y direction. To y. So then x cross y, yeah, x cross y is in the z direction. Okay. So dl in this case is going to be in the positive y direction. So let's just say this is equal to 0, dl scalar 0. And r, I can write that as the vector. It starts from here, it goes down a value of r in the x direction. So it's going to be negative r. And then it goes none in the y direction. And then z in the z direction. Okay, now let's take dl cross r. dl cross r is equal to the determinant of the following matrix: x hat, y hat, z hat. This is your definition of cross product. And now I'm going to put my components of dl right there. So I have 0, dl, 0, and then I'm going to put my r values right here. So I have negative r, 0, z. So when I take the cross product, I'm going to expand about this row. So I'm going to take x hat, and let's just put that as my first value. X hat is going to be dl times z, dl z minus 0. Okay, now for the y hat, I'm going to get 0 times r, 0 times z, so it's 0. Now for the z component, I'm going to get 0 times 0 minus dl times r, so it's going to be r dl. Okay? Now, here, sometimes when you solve problems, there are tricks, and you got to kind of know the tricks. And in this case, the trick is to use the symmetry of the situation. So if I have a piece right up at the top, I also have a piece right down at the bottom, and it has this vector for r. So this bottom piece has dl equal to 0, negative dl, 0, and r is equal to r, 0, 0, z. So if I do dl cross r for this bottom piece, I get dl cross r equals x hat, y hat, z hat. Now I have 0, negative dl, 0. And then the bottom one I have r, 0, z. And I'm going to get my x component, I get negative dlz. My y component, I get 0 again. My z component, I get this time, I get plus dl times r dl. Now, and you'll notice that I'm going to be able to add the magnetic fields due to these two pieces together. And so I'm going to have this contribution from the top piece and this contribution from the bottom piece, and they're same except for the x component is negative in this case than it is that way. So these two x components are going to cancel. So really, if I combine these two together, then I just get the RDL terms. Okay, so that means that when I do this up here, the only surviving things for every single piece, since it always has a piece on the other side using symmetry, is going to be RDL. Okay, so, and in the z direction. So now I can write this. dB, I want to draw my circle again. Let's draw it like this. So that's R, and that's Z. So dB Z is the only surviving component. It's going to be mu naught over 4 pi. And now and then I have I. Then dl cross r hat, I already said, was just going to be r dl. Now I need to divide by r cubed. So this is r. So that's a right triangle. So r is going to be the square root of r squared plus z squared, because it's a right triangle. So down here, I need to raise that to the third power. So I'm going to write this as r squared plus z squared to the 3/2, because I'm taking the square root and I'm cubing it. Okay, so now that's the contribution to each piece. Now I need to find the contribution to all pieces. So I'm going to integrate both sides. So I get bz is going to be the integral of mu naught over 4 pi I r dl over r squared plus z squared to the 3/2. Now, what changes as I move around this loop? Well, this constant doesn't change. I haven't put the limits of integration on purpose, okay, because we don't need to. R doesn't change. That's the radius of the loop. this is the same r. Z is a parameter, right? It doesn't change for this particular location. So the only thing that this changes is the dl. So I get this, mu naught over 4 pi I r over r squared plus z squared to the 3/2 integral of dl. So if I integrate dl around that whole loop, what would I get? Well, that if I add up all the little pieces along that loop, I get the circumference of a circle. So this should be the circumference of a circle, which is 2 pi r. So then that means I get bz equals mu naught over 4 pi 2 pi r. I have another r. So it's r squared. Oh, that's right. Okay. Over r squared plus z squared to the 3/2. Is that right? That's right. Okay. That's the right answer. Now, even though we knew it was the right answer, we can kind of check these things in general because what if I'm at the center of the loop? What if z is equal to 0? Should there be a magnetic field? Well, yeah, because each piece is still going to make a contribution to the magnetic field, and if I let z go to 0, I still have a magnetic field, okay, in the middle. I feel like we want to look at the limit of z very large. So if z is very large compared to r, then for large, so let's put large z. Then I have this term on the bottom is this going to be z squared to the 3/2 or z cubed. And that r term is insignificant. So now I get mu naught over 4 pi 2 pi r squared I over z cubed. And this is important because once you have a 1 over z squared term, 1 over z cubed, this looks like E due to a dipole. Okay, because that's 1 over r squared along the axis of the dipole. So this tiny little ring of current acts as a magnetic dipole, and that's pretty important. But we'll get to that. And this also, pi r squared is the area of the loop. So pi area times the current is the magnetic moment. Okay, but now let's switch over to Python and let's do this exact same thing. Now, before I do that, I need to pick some values. So let's say, how big is my loop? Let's say, I'm thinking in my head, it's like, how big is the loop? It's about 5 centimeters. It's kind of big. 1 centimeter? 2 centimeters. So R is 0.02 meters. I is 1.5 amps. And then let's say Z equals, let's have it pretty close. Let's say Z is equal to 5 centimeters, 0.05 meters. So those are my parameters I'm going to use because I'm going to do a numerical calculation. I have to have it that way. Okay, I'm going to have to switch back to this paper because let's go ahead and think about. So I didn't switch back. I just never left. So let's think about how we're going to make this loop. So here is my circle. I'm looking at the loop now. And I want to put a piece right here. And then, so the first thing I'm going to do is say n equals. How many pieces am I going to break it into? And let's just say 8, 10, 8. So n equals 8. So that means I can put my first piece right here. And then this is the radius r. And then I can break this into angles, right? So this is some angle theta, where d theta, the angle between each angle, is going to be equal to 2 pi over n. So then if I have if I want to find an arbitrary piece right here, I could say its r value, which I'll call r wire, is going to be equal to, and let's call this again the xy plane, which I don't know why I did it that way, but so this location would be r times cosine theta sine theta 0. If I get the x and y components of that, I can use that angle and that value r. And then what I can do is say theta equals theta plus delta theta and move to the next angle and do it again. So I can find all my pieces where they are by increasing theta. Now, what about DL? How do I find the direction of DL? Because see right here, DL is that way, and here DL is that way. So there's a couple ways to do this. Let's just think about this. If I did R cross Z, since I know the axis, let's just do DL equals Z hat cross R hat times 2 pi R divided by N. Okay, so if I have this as Z hat, and that's R hat, and I do Z hat cross R hat, R wire hat, like that, then the right-hand rule, it would be pointing in that direction. So that gives me the right direction. And then the length of that wire is just the total length of this whole wire divided by the number of pieces. So it'd be 2 pi R is the circumference around the whole thing divided by N. Okay, I think that's going to work. So now what I can do is I can make my wire out of all these pieces, and they all need to have an angle, a direction for the wire. And then I can calculate the magnetic field due to each wire using just delta B equals mu naught over 4 pi I dl vector cross the vector from the wire to the observation location. That's an important point too. Divided by R cubed. So if you look at this from the side, here's my wire, here's my piece, here's my observation location RO, and this is R wire, and that's R. So R is going to be RO minus R wire. Okay, let's get to it. We've wasted enough time on paper. Let's get to the programming. Computer view. There we are. Okay, so switch over here to Python. And let's just go ahead. And I used this before. I'm going to call it Km equals 1 times 10 to the negative 7th. That's my mu naught over 4 pi. And that's one of the things in the solution. I used the solution from Matter and Interactions textbook. And it likes to keep mu naught over 4 pi as one thing because it's an exact value of 10 to the negative 7th. Let's put in my other values. R equals 0. What did I say? I said R was 2 centimeters, 0.02. And I said I was 1.5. I am 1.5. And then Z is 0.05. Okay, so let's build our wire. So N equals 10. Theta equals 0. D theta equals 2 times pi divided by N. Okay, so now I'm just going to say, let's do this. N equals 0. That's my counter N. This is the way I like to do it because I think it just makes more sense for people. Now I'm going to say while N is less than big N, do the following. Number 1 is to make a wire piece. For my wire pieces, I could make them actually cylinders, but I'm going to make them spheres instead. So I know that's weird, but just it doesn't really matter what it looks like. So let's just say, let's first find the location of that. So R wire is going to be equal to R times the vector cosine theta, sine theta, 0. Oh, I need this. I'm just making the wire right now. So what else do I need? I can make the sphere now. Let's just draw a sphere. I'm not going to label it or give it a name. I'm just going to say sphere. Position is RW, and the radius is going to be equal to, let's say, 0.001. And then I'm going to increase N equals N plus 1. And let's save it. Magnetic field due to loop. Okay, and run it. And I'm going to get rid of the camera so that you can see. And there is my one. It only made one. Why did it only make one? Aha. I never changed theta. I made 10. They're all just right there. Okay, so after I make that sphere and after I add 1, I'm going to say, actually, I could just do, I could do this. Theta. Okay, let's do theta start equals 0. And then, so this is going to be theta start plus n times d theta. So then I'll start off with n equals 0, and that means theta start is 0. And then I just add that value in there. I don't actually have to increase theta. I don't know. You could do it either way. I kind of like it this way, though. Okay, now let's try it. I didn't save it, but there you go. Okay, let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Boom, got it. 1. Okay, so now I can change this to 100 if I want to, and then you'll see it actually looks like a ring. And this is a 3-dimensional ring because this is Python. Oops, I can zoom in and out. I can rotate it. See, cool. Okay, so that is making the ring. Now let's go ahead and put our let's say it's RO equals vector 0, 0, Z. That's my observation location. And let's go ahead and put a point there. So ROBS equals sphere, position equals RO, radius is going to be 0.001, and let's make it yellow. Color equals color dot yellow. Okay, let's just run that. I still haven't saved it. And that looks huge because it's coming right out of this. I guess it's fine. Okay, let's save. So now I just want to calculate I need to calculate DL. I'm looking at my little script here. No. Yeah. Okay, I'm going to need to calculate DL. So let's just go down here. The sphere is just for looks. That doesn't really do anything. So DL is going to be equal to the cross product of vector 0, 0, 1, that's Z hat, and RW hat, which would be norm RW. I feel like I should check these. Let's go back to 10. And then I have to multiply that by 2 times pi times r divided by n. Let's go ahead and put an arrow there. So I'm going to say let's just put an arrow. Arrow, position equals RW, axis equals DL. I think that'll work. Let's just see. Let's make it yellow. I really want to check and make sure. Okay, there you go. So that actually is artistic. I really like that. So here you can see that that's the length is the length vector, and these do look like they all add up to the circumference of the circle, and they're in the correct direction. That's a win, and it's pretty. I don't want to get rid of it even. What if I change that to 100? What would it look like? And you can't even see them. They're too small. Okay, that's fine. Let's not put those. We don't need to see those. So now I can calculate the contribution to the magnetic field, but in order to do that, I need to first say this. B equals vector 0, 0, 0. So what I'm going to do is calculate the contribution from each little magnetic piece, each little wire, and add it to that. But I need to start with the value to add it to. So down here, I'm going to say dB equals Km, that's my constant, times I times the cross product of, I need to find R. So let's put it right here. R equals RO, the observation location, minus R wire, the wire location. That's going to change each time in the loop. So now I can take the cross product, IDL cross R, divided by mag R cubed. Now I can add that. What happened here? Okay. Okay. Now I can add that, B equals B plus dB. And then I should be done. And then we can go down here and we can say print calc B equals B, Tesla. Now let's do the theoretical. B theory equals, I'm going to type in my equation, which I have, it's mu naught over 4 pi, Km, times 2 times pi times r squared times I. I hate that. I'm going to put my I over here. I always get paranoid if I put r to the 2 times I think it's going to raise it to the I power. It won't, but I'm afraid. Divide by r squared plus z squared to the 3/2. And print that. Print B theory equals B theory Tesla. What do you think? Think it's going to run? I don't know. Saved. Run. Error. Inconsistent line DL. Oh, yeah, see up here, that's what happened. So let's, these all got shifted down. Okay. If you're not familiar with Python, it's space tab oriented, so tabs matter, which is a little weird, but at least you don't have to put all those curly braces everywhere, which is just super weird. Okay, so here I have, okay, I got the same thing. So this is great though. Look, I calculated the vector magnetic field, and it's in the z direction. And you'll notice that my x and y components are not 0, but they're 0, right? I mean, 10 to the negative 22, that's 0. And for the z component, it's pretty much the same thing. So that's pretty nice. Now, let's do this. Let's put an arrow there. So let's say B scale. So I want to draw an arrow for the magnetic field. So I need B scale equals, let's say, 1 times 10 to, no, 1 times 10 to the negative, 1 times 10 to the 5th. Let's try that. And then I'm going to say B arrow equals arrow. POS equals RO. It's the observation location. Axis equals B scale times B. Color equals color dot cyan. Okay, let's run that and see if that works. Oh, it's huge. So I need that smaller. So let's try 10 to the 4th. It's still pretty big. That's fine. But there's my magnetic field. Okay? And that's a win. Now, what if I want to find the magnetic field at some location up here? What if I change the observation location to ZZ right there? Well, nothing changes in this program. I mean, it's still the same. And there you have it. There's my magnetic field. It's much smaller in magnitude and it's pointing in that different direction. What if I put it right up here above the thing? So that would be in the, let's put this, that's on the XY plane. Yeah, this is 0. Okay. Check that out. That's just pretty cool. Okay, I need to do one other thing. Let's put this back down to 0 where it was. Oops. 0Z and run it. Make sure it's working. Now, what if I change this to only 10 points? What happens? Then it's still not bad. Look, I'm getting still close to the same theoretical value. So it looks like it's working. So let's change that back to 100. And I think I'll end there. I'm pretty happy. The next thing is to show that this is a dipole, and I'll do that in another video by making a function. Only run this and save it. And I'm going to give you the code. I'm going to give you some other things. But that's that. I'll talk to you guys later.